The topic we're considering right now are Stirling numbers of the first kind. These are related to permutations, and we're going to build up a recurrence relation for them. So as motivation, let's go back to permutations. So if we can think about building up a permutation of n from permutations of Sn. So build a permutation of n from permutations of n minus 1. And this is how we get a recurrence relation for Sn. So if we think about having a permutation of n, so let's do an example, and we'll let n equal 8. What's a permutation of 8? Well, I'm going to write it in one line notation for this example. 5, 2, well, let's make it 8, 2, 3, 6. So that's a perfectly good permutation. And we can think about how many ways can we add 9 to this to make it a permutation of 9. Well, I could put the 9, so where to put the 9. I could put it here in front of the 4. I could put it here after the 4, after the 1, after the 7, 5, 8, 2, 3, 6. So in general, there are going to be 8 plus 1 positions for the 9 to go. And the upshot of all of this is that when we generalize this off of n equals 8, we get the formula that the number of permutations of n is equal to n times the number of permutations of n minus 1. And of course, if we use our base case that S1 equals 1, then together these prove that the number of Sn is equal to n factorial, which is maybe the definition of it. So we want to use the same idea anytime we have permutations and we're trying to get a recurrence relation. The idea is, how do we build up to the next level? If we're thinking about Stirling numbers, let's put those in black. The signless Stirling numbers are the ones that I'm going to do. These are defined as follows. C of nk, here n and k need to be positive integers. This is going to be the number of permutations, W, in Sn, such that W has exactly k cycles. And what we want to think about is building up permutations where we focus now on the number of cycles. So of course, the one line notation that we're using here is no longer the right thing to use. What we want to use is cycle notation. So let's just take a moment to do our example again and convert it to cycle notation. So when I'm doing cycle notation, I can think about, okay, I write the letter 1. 1 goes to 4. 4 goes to 5. 5 goes to 8. 8 goes to 6. 6 goes to 2. And 2 goes back to 1. So I want to put my orientation on this so that we're clear. This is one of the cycles. I only have 6 letters in this cycle, so this isn't the only one. So I'll start with the letter 2 because I haven't done that one yet. Where does 2 go? 2 goes to 1. Oh, yes, I've already done 2. Sorry. 3. I haven't done 3. Looks like 3 goes to 7. And of course, 7 goes back to 3. So this is my permutation written in disjoint cycle notation. Now think about, how can I augment this to get a bigger permutation? If I think about it in cycle notation, again, I want to think about where to put the 9. And of course, there still should be 8 plus 1 possibilities, but now let's think about what happens to cycle type when I put those in there. So one thing I could do is I could put the 9 here, or I could put the 9 here. So if I put it on this side, then I get the cycle 3, 9, 7. And if I put it on this side, I get the cycle 3, 7, 9. And those are indeed different. And now what we want to do is say, okay, well, let's do the same thing over here. I could put the 9 here, 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 or here, and these are all different. How many choices do I have? Well, for a transposition, there were 2 choices, and for the 6th cycle over here, there were 6 choices. But there's one additional choice because that only gives me 8 in total, and the other is to put the 9 here and have it go to itself. That last one adds a cycle. These two don't. So that gives me the intuition to go ahead and write down my formula for the recurrence relation for C in K. So C of nk, well, maybe we'll call this a theorem. C of nk, and again, I'm trying to relate it to n minus 1, so I get to use the Cn minus 1 numbers. If I put it on any one of these positions, I have not changed the number of cycles, right? And there are n positions, because this is my full permutation that I had for n minus 1. So there are n minus 1 edges I can think of where I can add my permutation, or my letter n, and I fixed the number of cycles. Or I could do the case that's over here where I create a new cycle, and there's no choice in that. So I get n minus 1, k minus 1, because I still want to have k cycles at the end. And now our proof, if we want to go back and write the proof after we've sort of done the reasoning, well, we have build a permutation of n by adding n, the letter, to a permutation of n minus 1, either by, that's going to be our plus, adding n to an existing cycle, or creating a new cycle for n. And this, there are n minus 1 ways to do it. And here there's one way to do it. And now tracking the number of cycles gives us our end result. So this is a really powerful recurrence relation for Stirling numbers of the first kind. Again, this is the signless version. In the signed version, we would keep track of the parity of k. But in the signless version, we have this nice recurrence relation, and we build it up in just this way.